Hello and welcome to General Relativity Parallel Transport Part 3. Now, in Part 2, this is basically just a recap. In Part 2, we looked at the covariant derivative, and I'll just remind you what the covariant derivative is. So if I write that down, covariant derivative. And that is expressed by dv, so the derivative of the vector with respect to the general coordinates xi. And that is equal to d, if I can make that look more like a d, dv superscript k by dxi. And we've got an additional term which is plus Vj gamma Kij, right, like that. Now, we put parentheses around that and multiply by the basis vectors Ek. So this, as it turns out, will be a series of ordinary differential equations, most of which are rather difficult to solve if you can do so at all. But as you might remember me saying in the last video, the trick is to make a non-linear vector field where all the vectors are sort of all over the place and certainly not linear. The trick is to create a case where all of those do become effectively linear, like that, so that they are parallel to themselves. Yeah, and you achieve this from this. So you achieve this case from this case by equating this to 0. And in equating that to 0 and finding formulae, particularly for the Christoffel symbols, that satisfy that equation, meaning that for those solutions that you find, that will always be 0, so that will always be 0. And that's what you want to try and achieve. If you can get the covariant derivative on the left-hand side as close to 0 as possible, you have achieved a case whereby you have made what is essentially a tangential velocity at every point on a curve parallel to itself, and that's really what you're doing when you do that, so that that looks, well, a lot straighter than it would be generally. Might not be possible to achieve an absolutely straight line like the line created by a ruler, but you might get something like a geodesic, which is the straightest curve you can have, and it's the sort of curve that aeroplanes fly on to minimise fuel costs, fuel itself, and operating costs and everything else, and of course you get there quicker. So that is that in a nutshell. Now, I want to say a little bit about the Christoffel symbols before we move on. I've already mentioned these, I think. It's the gamma superscript K subscript IJ. Now, there's two things, well, there's actually a number of things to say about these. What we find when we start working out these Christoffel symbols, that we get a number of Christoffel symbols, and you might get a 1, a 1, a 1. You might get a Christoffel symbol with a 1 and a 1, 2 there, a Christoffel symbol with a 1 and a 2, 1, a Christoffel symbol and a 1 and a 2, 2. And then what you might get is a gamma 2, 1, 1, gamma 2, 1, 2, gamma 2, 1, and a 2 there, 2, 2, 1, and a gamma 2, 2, 2. Now, what do these 8 Christoffel symbols mean? Well, basically, they are measures of the basis vectors, and in particular, these Christoffel symbols would be a measure of how much the x1 basis vector, which we call E1, we need. And these on the second row down would be a measure of how much of the x2 basis vector, E2, we need. Now, I'll write that down for you so that you can actually so that you actually have a written definition. So these are the ones that are particularly important. The Christoffel symbol, gamma superscript 1 ij, is, in fact, actually, I'll just shorten the sentence a little bit. So this tells us how much of the x1 basis vector so that will be the E1 basis vector that we need. There you are. Gamma superscript 1 subscript ij tells us how much of the x superscript 1 basis vector E subscript 1 that we need. So if you're talking about some axes, x1 might represent theta along here. So we'll just write theta down for the sake of argument. So gamma would be some measure of that axis, if you like. And in particular, gamma 1, well, you might write gamma theta, but we're setting theta as the first axis, if you like. So we'll keep that as theta, and we'll just write 1 there. It's almost like talking about place value. Theta has place value of 1. Phi has place value of 2. So if phi is coming down here and you've got a basis, you've got a Christoffel symbol which indicates the measure of that basis vector, or the basis vector for phi, then that would be gamma 2 ij. And of course the basis vectors are actually written E2 like that and E1 over here. So gamma 2, just like the one above, tells us how much of the x2 basis vector, this time E2, that we need. Okay? So it's almost like talking about, you know, if you say, well, I need, I don't know, a quarter of a 10-meter length of rope, probably to hang myself with. Just a little joke there. But Yeah, a quarter of a 10-meter length of rope, then it would be a quarter times 10, wouldn't it? And that would give you whatever it gives you. So 2.5. So it's a bit like talking about that sort of thing, but this is more complicated, obviously. Now, how do we determine what these Christoffel symbols are? I can't remember if I mentioned in the last video the type of functions that the Christoffel symbols might yield, that you might have to substitute in there for the Christoffel symbols. But I'll just run through a few. So a lot of them are just zero. So a lot of them are just zero. You can have trig functions, which is what a lot of them are, as it turns out. And you might actually have constants. But not just constants or other variables. I'll just put vars for variables. So gamma, the Christoffel symbol, gamma, might be zero for a lot of them. You remember the 8 that I wrote up there? There's about 5 of them that are zero and 3 that are not. And the 3 that are not are all trig functions for the example we're going to do anyway, or for the theory we're going to do. In some cases, they're constants or other variables. So you might have, if you're considering variable height or something like that, then you might have a row which is variable, or it might in some cases just be constant. So if they're constants, it makes this equation a lot easier to solve. So the equation for the gamma, the Christoffel symbols, and I'll just write that down. So the gamma ijk is equal to this expression, dej by dxi. Oh, excuse me, it's in the wrong place. The I goes down there, it's sub I this time, but you'll see why that is eventually. EI, because these are basis vectors, dot GLK. LK, not 1K. Right, and that's the expression that we use to find the nature of the Christoffel symbols, whether they are zero, constant, or trigonometric, or variable in some other way. So the partial derivative of EJ with respect to the partial derivative of x sub I, so anyway, dotted with E sub I, and then you multiply by the GLK. But what are the GLK? Well, the GLK is actually a matrix. It's actually, well, to all intents and purposes, in our case, it's a 2 by 2 matrix, and it has entries of G11, G12, G21, and G22. So these are all the components of the GLK, the G superscript LK. And so these should all be superscripts. Now it turns out, and I'm going to mention this now because we need to know it, and so that hopefully we understand what we're doing more coherently than we would otherwise. The GLK is obtained by finding the inverse of the G sub LK. And this is a matrix similar to that, but we have to find this first before we can find this. And then we can work out this once we know what the GLK are, and then we have our Christoffel symbol. And that's what we're ultimately going to do. But first and foremost, we're going to work out the G sub LK, then the G superscript LK. And we'll leave that probably until the next video, working this part out in parentheses, and thus therefore work out the Christoffel symbol. So we'll do that probably in part 4. Now I want to make a stop, because what we have to do is to convert all our x, y and z coordinates to spherical polar coordinates. And the best way to do that, if you don't already know, is to draw a globe, like so, a globe. Now this is a 3D globe on a 2D plane. The whiteboard is a 2D plane. So you have to kind of use a bit of artistic license when not only drawing this diagram, but actually understanding it and interpreting it. So we have an axis which we'll call Z, and we have an axis going up here horizontally. Now normally that would be referred to as the y-axis, and this axis coming out here would be referred to as the x-axis. You can draw that if you want, and work what we're going to work out yourselves using this configuration. But I am going to label this axis as the x-axis and this as the y-axis. Okay? Now, we take a point on the surface of the globe, and if my pens haven't dried up by now to leaving the tops off, I should be able to draw a coloured line. So we'll draw a red line joining the centre of the Earth, or the origin if you like. It's half red, half black is that. And we'll call that, well, I'll tell you what, we'll draw the rho there. Rho is just the length of that radial vector from the point of the centre of Earth to that point on the surface. And of course there's an angle, theta, between that line and the vertical Z. So we've got rho, the length of that radial vector, joining the centre of Earth with a point on its surface, which we'll call P. And that point P is just an angle of theta with the vertical. Now, we still have a little bit more to draw on, because along that point P is always going to be on, what is it called? A line of latitude. So that green curve is a line of latitude, and you get them all round Earth like that. And you also have lines of longitude, like so. I'm going to try and get one going through that point. Okay, so I've drawn them, but not very expertly, but hopefully you will bear with me. Now, I'm going to continue to draw in this part of the line and this part of the longitude line, and I think we'll take it some point that ultimately, if you draw a line like that, goes up to the x-axis, and we'll join the centre of Earth with that point on the surface of Earth, usually. Yeah, I think it would be. And I'll, for your benefit, just drawing another line of latitude. So it's important to remember, and in fact to understand, that there is another angle in this, and it's angle phi, and it's that horizontal angle between this line and the x-axis. So if you think about the x and y axis describing a flat plane like that, so that angle phi is actually in that plane, and the angle theta is, well, it's perpendicular to that plane, isn't it? So we can now start to work out what our x, y and z coordinates actually are. So I'll write down here, we want to work out what x is, rather than it just being an x for the x-axis. The same for the y and the same for the z. Now, we'll start with the z because that's the easiest. If you want to work out what the z-axis is in polar coordinates, you just resolve this radial vector, rho, with respect to the vertical axis z. So that becomes, if that turns through that angle theta, this length up here becomes rho cos theta. So that is rho cos theta. Now we'll start with x. It doesn't really matter whether we start with x or y, but x makes sense. So if we do the same with rho, but in the opposite direction to get down to this red line here, then we have rho cos 90 minus theta, rho cos 90 minus theta. But we don't want angles like that. But if you've done high school level mathematics, you will realise that that's actually rho sine theta. So that is what that red line is there. Now, we can't just have that red line sticking out there doing nothing. We have to do something with it. And what we're going to do is resolve it through angle phi to give us the x coordinate, the x polar coordinate. So we've got rho sine theta along here, cos phi. So we've got rho sine theta cos phi. Now, exactly the same for the y-axis, so you'll get a slightly different expression. We've got rho sine theta here, and when we resolve it along the y-axis, we get rho sine theta cos 90 minus phi. But we don't want angles like that. So we can rewrite this part as sine phi. So what we've got is rho sine theta sine phi. Okay, we've got our polar coordinates here just by drawing a diagram and resolving them all. Now, there's something else I want to mark in on the board, because I mentioned the radial vector, and of course it is a vector really. If that point's moving, it's moving really in 3D space because it's a curved surface. It's not just a flat surface, in which case it will be 2D, 2 dimensions. This is 3 dimensions because it's also the 2 dimensions of the plane combined with the fact that that plane is curved. So it's really a 3D space. And that vector, which we can call R, we'll just call it R with a line above it and an arrow. I don't know what you call that. but that position vector has Cartesian, not in polar coordinates, in Cartesian coordinates. That position vector is x, e, x plus y, e, y, e sub y. That's supposed to be an arrow up there, not a very satisfactory one, plus z, e sub z, I hope. Yeah. Now, if you remember back to your high school days, this might look similar to something that you did learn in vector calculus. You know, if you studied A-level mathematics in England or Scottish Highers in Scotland, or any equivalent qualification in any other country, you might be familiar with that, because what these basis vectors are really are they represent effectively. I'm going to draw it like this. I'm going to draw this the right way round now. In high school mathematics, you would have your I coordinate along there. You would have your j coordinate along there, and you would have your k coordinate. What am I doing? They're supposed to be vectors. So you'd have your k vector going vertically upwards, and of course, actually, you've got the axes really doing that. So that if you had a position vector down here with the coordinates 1, 3, and -5, then that the position vector joining the origin and that point there, P, would be R equals, it's a bit small, isn't it? Let's rewrite that. You would have R equals I plus 3j minus 5k, right? Well, these basis vectors, e sub x, e sub y, and e sub z, are just a very close analogy to the I, j, and k's of ordinary high school level mathematics. And that's basically what they represent. So, for example, if you see pictures like this in General Relativity, you'll have your x-axis and your y-axis, and then your basis vectors E, Y would be in these kind of directions, right? And that's why we write position vectors or velocity vectors or whatever in General Relativity in this sort of language, in this sort of terminology. Now, I'm labouring my points a little. We want to make some headway. So let me just erase these graphs off the board. Now, to convert that position vector into the polar coordinates, all we have to do is substitute rho sine theta cos phi in for x, rho sine theta sine phi in for y, and rho cos theta in for z. And so what we get is, I'm going to write it up here because I think we'll need it. We've got our position vector r equal to rho sine theta cos phi, and that's multiplied or whatever with the ex basis vector, plus rho sine, and I better rub, where have I put it? There we are. Just rub that off. Plus rho sine theta sine phi e y, plus rho cos theta Ez. And that is our position vector of that point on the sphere that I've just rubbed off. That is a position vector of that point. Now, I like to write this as, this just makes it a little more compact. I tend to write it, I think it's okay to write it like this. It's another vectorial form, but you can just eliminate the basis vectors and just write these components here with a comma between them. So you got rho sine theta there, sine phi, and we've got rho cos theta there. Okay. Now we've got something substantial there, because we now need to, if you remember, I mentioned the derivative of something with, did I mention something doing the derivatives with respect to theta of y? I can't remember. I better just define what we need to do next. So basically the derivative with respect to theta of all of that, and it's a partial derivative of all of that with respect to theta. So dr by d theta is actually equal to the polar basis vector e theta. And the derivative, let me just get that right, the derivative of r with respect to phi is just equal to e sub phi. So that would be like the polar basis vector in terms of phi. Now, to find e theta, we just differentiate with respect to theta all of this. So we've got rho sine theta cos phi, and I'm going to separate it with the commas because I just think it simplifies it a lot more. And then we've got rho sine theta sine phi. That would be the y component, if you like, and the z component would be like your rho cos theta. Yeah, if I put the basis vectors in with the plus signs in between, that would have been right up to there, and I really want to conserve space, so I hope that's okay. So we find if we differentiate all of that, we've got e theta is equal to, well, if you differentiate this first bit here with respect to theta, you hold the cos phi constant. So the cos phi doesn't change, and the rho doesn't change, but the sine theta does. And what you get is rho cos theta in the new vector. Differentiating this similarly with respect to theta, we get rho cos theta, and the sine phi stays alone. And this differentiates to, well, it's going to be minus rho sine theta. Okay, so we've got our first spherical polar basis vector, or I can't remember exactly what people call it. Anyway, that is the correct expression there. In fact, I ought to just double check that. So we've got e theta cos cos, sine, and minus. Yeah. Now for E phi, you do exactly the same thing. You differentiate each one of these with respect to phi now, or the function of phi. So I'm not actually going to write this bit down because it's consuming time, and you know, it's important to be succinct. So if we differentiate this bit, we get rho sine theta, because we're keeping the theta constant this time, the sine theta, but we differentiate the cos phi. And of course, I haven't left enough room there, so we've got minus rho sine theta, I'm writing it out again, sine phi. The cos phi goes to minus sine phi. And then this differentiates to give rho sine theta cos phi. Sine phi goes to cos phi. And what does this go to? Well, that's just treated as a constant when differentiating with respect to phi. So that just disappears. And we get 0. Right. So we've got two important expressions here, because we now, how do I put this? Well, do you remember just a short while ago during this video, just after the start, I told you that G LK is equal to G11, G12, G21, and G22. Well, it turns out to find G, we have to form two matrices, which I'm going to call M and N. Now, but what are M and N, and how do we find them? Well, we know we need two matrices because if I write down G sub LK, not this one, but this one, because this is the one we've got to find first. And it has a matrix that has a similar form to that. It will have different functions in it though. Now, not only did I say this G superscript LK is the inverse of G sub LK, but G LK is equal to the dot product, I think we might, let me just, right, is equal to M multiplied by N. But what's M and N? Well, N is the transpose of M. So actually what we've got here is GLK equal to MMT. So we've got an original matrix multiplied by its own transpose, yeah? But we still have to find M. I keep saying this M, and yet what is it, you know? Well, it turns out that M is equal to the matrix E theta and E phi, right? So to get to this, we have to find this. But to find this, we have to deduce what matrix M is and matrix N. And it turns out that matrix N is just the transpose of matrix M, and we know that matrix M is just this matrix here. And what have we got? We've got E theta and E phi. So, if I write down that M equals, I'm going to put square brackets here. Right, E theta. So we've got, let me just write these in hopefully blue if I can find a blue pen. Yeah, here we are. Right, so writing these across the board, we've got rho cos theta cos phi. And now we don't put the commas in, we're just putting these components in as entries of the matrix now. So we've got a rho cos theta sine phi here, and we've got a minus rho sine theta here. And let's just close that matrix off. And then we write down E phi. So what we've got here is, I'm drawing the matrix too big, but never mind, gives us plenty of room. Minus rho sine theta sine phi. Leave a gap. You don't need to put a comma in because it's a matrix now. So we've got rho sine, my handwriting is going a bit wobbly. Let me try again. Rho sine theta cos phi and 0. What I'll do is I shall shorten the matrix to make it look a bit better. Right. So I'm going to have to rub the writing off the top of the board now, because we need to find the transpose of that matrix. And that hopefully shouldn't be too difficult if you've ever done matrices before. So let's just erase that and proceed with writing down the transpose. So MT, which we call the transpose, is actually equal to N. Is equal to, this time you do need to draw it a bit longer. You first of all write this row down, all of that row, as a column in the first column of that matrices. So we've got rho cos theta cos phi. There, we've got rho cos theta sine phi. And we've got minus rho sine theta. And then we write down the entries in this row, or this one here rather. We write this down vertically over here. So we've got minus rho sine theta sine phi, and we've got rho sine theta cos phi, rho sine theta cos phi, and we've got 0, right? Okay, so we've now got two matrices. We've got our M matrix and our N matrix, and we know that G sub LK is equal to M times N. So we're going to basically, well, I'm going to leave out actually doing the multiplying out. But let's just now rub this out, and we'll rub that out as well because you should have that. I'll write out how you should let me just see, let's put this in there. Right, so we've got GLK equal to M dotted with N, or M times N. Now that should look like it's best to really convert those to I's and J's. You can write it like that if you want it. It doesn't really matter, but it is really, you can leave it like that. So now we've got, I'm actually going to write out the matrices for you again, but I'm not actually going to do the multiplying out bit. So we've got rho cos theta cos phi, rho cos theta sine phi, and minus rho sine theta. Close that. This is the first matrix, and then we've got minus rho sine theta sine phi, rho, the gap there, rho sine theta cos phi, and 0 here. Now that's not all, because we need to multiply that by its transpose. And its transpose is, this does work out because I've checked it. So we've got rho cos theta cos phi, just like we did before. Rho cos theta sine phi, and minus rho sine theta. Right? Am I right? Cos cos, cos sine and sine. Cos cos, cos sine and sine. Yeah. And then we've got this transposed. Minus rho sine theta sine phi, rho sine theta cos phi, and 0. And if you multiply those out so that you get rho cos theta cos phi times this entry plus rho cos theta sine phi times this entry minus rho sine theta times this entry, then the first entry of the new matrix is, when you simplify everything, rho squared. So this times this plus this times this plus this times this eventually simplifies to rho squared. Now we do the same with that top line and this column. So we've got rho cos theta cos phi times minus rho sine theta sine phi plus rho cos theta sine phi times rho sine theta cos phi minus rho sine theta times 0. And it turns out the next entry is 0. And if you then do this times the first entry plus this times the first entry and 0 times the first entry in that transpose, then you get a 0 here as well. It's just simple multiplication of matrices. And then if you multiply that entry by that entry by that, and that entry by that, you find that you have rho squared sine squared theta. Right. Now, the inverse, and we've already covered this, I'm running out of board space, so let's put down here, since G, I, J, you could have still used the LK, it doesn't really matter. We're talking about the same matrix. Since G superscript IJ is equal to the inverse, I just put INV. Did I say the inverse? Yes. The inverse of G sub IJ, then all we have to do is invert this matrix, which you, if you've done a bit of A level, certainly degree level, you should have no problem with that. And we'll just quickly do that. So I'll have to rub this off the board. And we hope that eraser stays there. Right, so G superscript IJ is equal to the inverse of this. G sub IJ. So how do we find the inverse? Well, that is equal to 1 over the det. Let me write that so that that looks more like a D. So 1 over the determinant of G sub IJ right, multiplied by the matrix. Just trying to make a bit more room there. So multiplied by, we have to do something to this matrix before just simply multiplying that out by 1 over the det. So what we do is we place this entry in the first entry, and we move the first entry, which is rho squared, to this last entry, so that we get this rho squared sine squared theta, and we get a rho squared in this entry down here. Now, the zeros, as it happens, just still stay as 0. In actual fact, you normally negate what's ever there. You multiply by -1. But because they're 0, they're just 0. Right? But what's the determinant of this matrix? Well, the determinant of G sub IJ is equal to rho squared times rho squared sine squared theta minus 0 times 0. Right? The determinant of this is rho squared times rho squared sine squared theta minus 0 times 0. And that comes out to be rho to the power 4. And by the way, these are powers. These are squared terms up here, including the sine squared. They're not Einstein indices like these i's and j's. These are all Einstein indices, these i's and j's, particularly the superscript ones. They're not to be confused with squared or power terms or whatever, you know. So that becomes rho to the 4 sine squared theta. And if I just rub that off the board, then we can do this calculation. So we've got 1 over rho to the 4 sine squared theta multiplied by, See if we can squeeze it on. Rho squared sine squared theta 0, 0 and rho squared. That comes out to be equal to, well, I'll just do the calculation for you. Rho squared sine squared theta. Just in case anyone hasn't ever done matrices before, I don't want to assume that you do just know. So I beg your pardon if you do know, but we want everybody to be helped. And if you multiply all of that by 0, you just get 0. And there we get rho squared over rho to the 4 sine squared theta. So you see, I've multiplied all of that by each of these entries. And this just simplifies. We cancel everything out. That cancels to give 1 over rho squared. Then we get a 0 here and a 0 here. And that just cancels to give 1 over, let me just write that a little bit neater. Alright, 1 over rho squared sine squared theta. Right. So, we found out what the G superscript ij actually are. And it's a matrix, and these are the entries that will be important for working out the Christoffel symbols. So I'm going to leave it there for now, because I think this has been nearly an hour. So many apologies for that. I hope you can take the pace. Please do subscribe. Please do come back, look at my existing videos and further videos that I put up on the site, and all that remains for me to say is thank you very much for listening. Do come back and see you later. Okay, bye.